Print screen. Now see, this is chapter 2, our diode application. You can see diode application. So I will go down. So here we will understand the load analysis, how it is applied to diode network, become familiar with the use of equivalent circuit of analysis. Okay, I do not need that. Understand the process of rectification. This is very important. Process of rectification is important. Be able to predict the output response of a clipper and a clamper. Okay, that is important. Be familiar with the analysis of range of application of generator. That is also important. Now let's go down. Okay, before coming to this topic, we want to go to chapter 1 for a look at the characteristics curve. Okay, what do I mean by this? This is a characteristics curve of three different semiconductor. This one is for germanium. This is for germanium. This part is also for germanium. The middle one is for silicon. This middle one is also for silicon. This one is for gallium arsenide, and this one is for gallium arsenide. So what is this actually? This is actually current versus voltage. Current versus voltage graph of semiconductor diodes. What do I mean by that? In case of diode, what is a diode? Okay, someone is asking. So I can hear you, right? Okay, you should allow your computer audio. You should allow the computer audio. We need the video record. I am recording. Now here, what is the symbol of a diode? Let's go and see a symbol of a diode. This is a symbol of a diode. Remember, this is the symbol of a diode. This one is the structure. This is the symbol. This like the resistor has a symbol, capacitor has a symbol. This one will have a symbol as well. Okay. Now, this is the symbol of a diode. Now here, look at very carefully. When this was forward bias, the current would try to go from this point to this point. So current will go from this point to this point. Remember, current will go from plus to minus, like this. Current will go from plus to minus, like this. So current can go in case of forward bias. So current is going from plus to minus this way. Current will go in this way, like this way. That means this way, right? Plus to minus. So it can go. In case of reverse bias, see, oh my God. In case of reverse bias, current tries to go from this point to this point. That means oppositely. That means from this point to this point. So in case of forward bias, current tries to go from P to N. In case of reverse bias, current tries to go from N to P. So it cannot go because of the depletion layer. In case of forward bias, current will go from P to N. In case of reverse bias, current will try to go from N to P. So what is happening? What is happening? So if current tries to go from P to N, it is okay, it is fine. If current tries to go from N to P, it is not fine, it will be stopped because this is diode. So this voltage is called VD. This is called VD, and this current is called ID. Current of diode is called ID. So if we D Ali, I'm going to make you co-host so that you can approve people.
Yes, sir.
Okay. Now, if you plot the current with respect to voltage, this is your graph. Now, I will make a video how we can make this graph. And remember, it is not possible to get this part. It is only possible to get this part. So this is this part. That means these and these. This is the forward bias. That means this half is forward bias, and this half, that is the lower half, is the reverse bias. In case of reverse bias, it is not possible to visualize because there is that is microampere range. See, this is microampere current, picoampere, picoampere. So picoampere, microampere current cannot be seen in the real life case or in the simulation. It is not possible. But here, these are all milliampere. That means in the forward bias, we have milliampere, ampere. In case of reverse bias, we have picoampere, microampere. So reverse bias, picoampere, microampere, that is not possible to measure because that is very small. Now, what is this? When your voltage is increasing, your current will increase. At the beginning, when your voltage is 0, 0.1, 0.2, 0.3, something like that, 0.1, 0.2, 0.3, your current will not increase. Why? Because there is a depletion region. So you have to remove the depletion region so that the current can move, current can pass. For removing the depletion region, you need to apply a little amount of voltage. That voltage will make your depletion region disappear. That voltage will vary. In case of germanium diode, it is 0.3 volt, at least 0.3 volt. That means you need to apply more than 0.3 volt. In case of silicon, it is 0.7 volt. See, when it was 0.7 volt, before 0.7 volt, the current is significantly lower. Lower means your curve is small. Your curve is too small. After 0.7, your curve is rising. Got my point? In case of germanium, see, when your voltage was 0.3, the current is significantly lower. When your current is more than 0.3, your current is rising. This one, the black one. In case of silicon, see, for germanium, if it is 0.7, before 0.7, the current is lower because it is flat, like this. After 0.7, it is rising, like this. So this is the forward bias characteristics curve. Let's look another one. Okay, here they explained it better. Here, what is happening? Oh, no, not here. Here. See, this one is for germanium. When it is 0.3, before 0.3, it is significantly lower. You cannot consider that. After 0.3, it is rising. Rising means your current is increasing. That means your diode is conducting current. Okay, now one simple thing. What is actually diode? Diode is actually a valve. Do you understand valve? Diode is actually a valve. Valve means it will allow think in one way direction, right? Like water valve. What is water valve? So water can go in one direction. That means in one direction the water can go, in another direction water cannot go. That is a valve, one way road. So diode is a one-way valve for current. That means current can go only in one way. In another way, if current tries to go, it will be stopped. Like a traffic police. Traffic police, what a traffic police do? It allows the vehicle to move from one direction to another direction. But in opposite direction, it will stop the vehicle and it will make a fine. That's my point. So diode is that. So in case of silicon, the voltage is 0.7. That means you need to apply at least 0.7 to make your diode on. That means make your diode conducting the current. In case of gallium arsenide, it is 1.2. So remember this thing. For germanium, it is 0.3. For silicon, it is 0.7. And for gallium arsenide, it is 1.2. Here it is written already. For germanium 0.3, for silicon 0.7, for gallium arsenide is 1.2. In case of reverse bias, see, this is the gallium arsenide. That is the best one. Why? Because the longer it will go, the longer it will go, it is better. That means it can sustain more voltage. Here, written 50 volt, 100 volt, maybe it is 150 volts, something like that. That means it can sustain 100 volt in the reverse direction. That means if you give more than 100 volt, the diode will be damaged. And the so this graph is for gallium arsenide. The longer it will go, that means the furthest it will go, the better. That means it can sustain more voltage in the reverse bias. So this is the reverse bias condition. In case of reverse bias, here let's say it is 150 volt, it is 50 volt, it is 100 volt, it is 150 volt. That means it can sustain 150 volt. Sustain means you can give more voltage, more voltage, more voltage in the reverse bias. So smaller it is the ores, that is the germanium. Here germanium was the best in the reverse in the forward bias. Germanium was the best in the forward bias because it needed less voltage for activation. Gallium arsenide was the worst in the forward bias because it needs more voltage to activate itself. But in the reverse bias, gallium arsenide is the best because it can sustain more voltage than other two, and the current in the gallium arsenide are very small. This is called leakage current, or the reverse bias current, leakage current, it leaks the current. So the leakage current is very small. See, only 1 unit, very small. But in case of germanium, see this one, the voltage is small. That means it can sustain very small amount of voltage in the reverse bias, and the leakage current is also very big. So germanium is not good either. So gallium arsenide is bad in forward bias. Germanium is bad in reverse bias. That's why we choose silicon. Silicon is at the middle. Silicon, neither the best, neither the worst. That's why we choose silicon. Silicon is at the middle. Okay, I believe you understood. Now, okay. Now think about the breakdown region. What is actually breakdown? See, this is a silicon diode or whatever the diode it is. This is forward bias. Forward bias is okay. Forward bias do not have any problem. If you give any voltage, whatever the voltage you are giving, no problem, nothing will happen. The current will go. In case of forward bias, whatever the voltage you are giving, it will go, it will pass. But in case of reverse bias, the voltage matters. If you give more voltage, the diode cannot hold the increasing amount of current, because the more voltage you will give, the diode will feel more pressure. The more voltage, that means more pressure. When the voltage is too high, the diode will not be able to restrict. The diode will be too weak for that big voltage, and the diode will crash. Crash means the diode will be the diode will be broken. It will break down. It will break down, and suddenly avalanche will happen. Avalanche, remember this word, avalanche. What is avalanche? Avalanche means suddenly something is broken. Like okay, let me show you one thing. What is avalanche? You need to know this word. Okay, what is avalanche? Avalanche is this one or this one. You have seen this in the movie. You all have seen this in the movie. What happened here? Here, all of a sudden, some snows breaks in. All of a sudden, that means everything is okay. Everything is okay. Everything is still. For some reason, all of a sudden, all the snows are falling. That is avalanche. This one, avalanche. This is a breakdown in the snow. That's why it is called avalanche. Understood? So these phenomena happen in case of your diode as well. That means it holds the current, it holds the current, it holds the current, it holds the current. When the voltage is too big to handle, it will break and all the current will leak and move, tries to flow. This is a permanent damage of normal diodes. If your diode is normal silicon, germanium or gallium arsenide, this is a permanent damage. Remember, so you need to apply the voltage less than that. This is called breakdown voltage, VBV, or breakdown voltage. Can you see that? My connection is too stable, is unusable. Okay. Breakdown, this is called breakdown potential or the breakdown voltage, and it is given as VBV. Remember, whatever the voltage you are using, you need to apply less than that. That means if you are working with highest 50 volt of voltage, that means highest amount of voltage you can get is 50 volt. So you need to buy a diode that is more than that. That is more than that has a more breakdown potential or breakdown voltage. Remember this thing. And here it is written already. Germanium is 0.3, silicon is 0.7, and the gallium arsenide is 1.2. No, not necessary. Okay. Now here was this is a summary. Summary means when current tries to go from positive to negative, it is okay. The current can go. When the current tries to go from this point to this point, the current cannot go. So the circuit is open. Circuit will remain open. So that is reverse bias. Now going to the chapter 2. Where is chapter 2? This is chapter 2. Okay, now. Let's do a math. In this math, they said for the series diode configuration, series means the diode will be in series like this. That means you have a source that is E, it's 10 volt. You have a diode in forward bias. How we can say it is forward bias? Because plus is connected with plus. So it is forward bias. You have a silicon diode, silicon, it is written Si, silicon, and you have a resistor that is R. So three component in series. So E, Si, and R. Then for the series diode configuration in figure, employing the diode characteristics and determine VDQ and IDQ and VR. What do I mean by that? See, your circuit is given and your characteristics curve is given. So you need to find VDQ, IDQ, and VR. VR means the voltage of the voltage of the resistance. VDQ means the voltage of the diode. IDQ means the current of the diode. Now, always remember, this is a characteristics curve. It will vary depending on the resistor and the voltage source you are having. So you need to draw a load line and you need to find where your diode is working. What is the working point of your diode? Because since your voltage is not variable, since your voltage is fixed, since your resistance is fixed, so it will be somewhere here, not everywhere. It will be somewhere, let's say maybe here, or maybe here, maybe here. So somewhere it will be working somewhere here, because your voltage is not varying, it is fixed. Your resistor is not varying, it is fixed. So your current will be fixed as well. So current will not vary, current will be fixed somewhere else. So you need to find that point. So how to find that point? Remember, here we will apply a KVL. You all know what is KVL. KVL means Kirchhoff voltage law. Here we will be applying a KVL. So let's draw a word, WORD. Okay, let the words comes in. We will apply a KVL. Now, here we will apply a KVL. The source is E. So, okay, let's zoom it. E equal to, not equal to actually, E minus VD minus VR is equal to 0. Here we have three things. So this is your source, E minus VD minus VR is equal to 0, because this is a closed loop, 3 elements, 1, 2, 3, this one. Now here, remember this thing. So we need to find the equation of VD. So let's take the VD in this side, that means in the 0 side. So E minus VR is equal to VD. So if you take the VD that side, that is your equation. Remember, that is your equation, right? Now here, what is VR? So we cannot write VR because VR is the multiplication of I into R, right? I into R. VR is I into R according to the Ohm's law. E minus I into R. This is one equation for finding out the VD. Now, if we take VR in this side, that will be our equation. E minus VD is equal to I into R, right? So if you take VR in that side, that is our equation. If you take VD in that side, that is our equation. Here we have two equations. One is this one, another one is this one. So at first, we will use this equation. Come here. We will use this equation to put a point. Here, and we will use another equation to put a point here. So let's take your E is equal to 10 volt. Let's give 10 minus I. Remember, in this line, your I is 0. This line, your I is 0 because I is 0 at the starting, right? I is 0. In this line, your I is 0. The more it will go up, the I will increase. So in this line, your I is 0. So let's put 0 and R, whatever the R is, doesn't matter, is equal to VD. So this whole thing becomes 0 because it is 0 into something, right? So it will be gone. So your VD is 10. Where is 10? Let's say your VD will be 10 here, somewhere here, because it is 0 0.5, 0 0.8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Somewhere here, right? So your VD will be here. Now, let's put VD is equal to 0. Why? Because in this line, if you go up, in this line, your VD is 0, right? So if you put 0, this one will be vanish. Now find the value of I. So I will be E divided by R is equal to I, right? Equal to E is equal to 10 volt divided by, what was your 0.5, right? Kilo, that is your I, is equal to 20 milliampere. Because 10 divided by 0.5 is equal to 20 milliampere. 20 milli is here. So that was your point for 10 volt. That is 20 milliampere. So if you draw a line, that is where your line will cross. So if you draw a line, that is where your line will cross. Okay. Now let's see what they have done. So your VD is 10 volt. So if your ID is 0, your ID is 20 milliampere if your VD is 0. Remember, we put some 0 somewhere. Here we put ID is equal to 0. Here we put ID is equal to 0. That's why our VD is equal to 10. Here we put VD is equal to 0. That's why ID is equal to 20 milliampere. So 10 and 20 from this equation. Remember, from this equation. Okay, remember, do not write VR, write I into R. From this equation, we got those two values. So one is 20, another one is 10. So if we they didn't show you the load line here. So let's show the load line like this. Oh my God. Now see this one. Your ID was 10, right? Let's say your 10 is here. And this is your point, 10 point. Because this is 0.5, this is 0.8, 1 will be here. Let's say this is your 1. At the middle, you have your 5. Let's say this is your 10. Right? And your 20 is this one. So if you draw a line in between these two, so that will be your load line, because you are putting at 10 and you are putting at 20. This two is your point. From where we got this 2 point? From here. Your VD is equal to 10 and your I is equal to 20. These two value, this 10 and this 20, these two value, we will put it, and we got our load line, and it will intersect the characteristics curve here, remember that is your Q point. Q means question point. There is your Q point. What is your Q point? You can see something is written Q, right? Q means your operating point. Here we already got our Q point. Where is that? This is our Q point. This is our Q point. At the Q point, if you draw a line, what is the value of our current and what is the value of our voltage? Remember, this was a free graph. If the 10 volt was somewhere here, then the graph would look like this. If the 10 volt was much further away, then graph would look like this. So this was a, oh my God. This was a free, oh, let me erase that. Okay. So this is your graph. So if your point is too close, that will be your graph. If your point is too far, that will be your graph. So I made an assumption. So when you will have the original graph, then you can draw the, you can get the actual value. So what value we get if you draw the line? The value will be 18.5. That means like this. So let's say if you draw a line from here to here and here to there, that is your I and that is your volt. For I, they said it is 18.5 and for voltage it is 0.78 volt. That means this voltage is 0.78 volt and this current is 18. So I have shown you something around 16 because maybe because my graph was not okay. Maybe because my 10 volt is not here, not so close. Because if it is this much is 1, so how can it be 10? So this 10 should be much further away. So this is your graph. This is your point actually. So this is your point. So your 10 is much further away here, and this is your 20. So if you draw a line, okay. Now here it crosses at around 0.8. Here it crosses around at 18.5 or 18.75 or 19. So that is your answer. So this answer can be approximated. So you can, whatever you write, no problem. If you write 19, I will give you full mark. If you write 0.8, I will give you full mark because that is for based on assumption. Now, if it is 0.78, they have written 0.78. If your VD is 0.78, if your VD is 0.78, so how much is your VR? Your VR should be 10 minus 0.78. 10 minus 0.78. That is your VR. So what is your VR? Your VR must be 10 minus 0.78 because that is the KVL. You have 10 volt minus 0.78, you got the remaining here. So your VR is the remaining. So how much is that? 9.22. That is one example. So I hope you will practice this type of math. Okay, this is the graph. That 10 volt. Okay, this is the solution. So I actually did a lot of hard work for drawing that, but it is here. So what you should do? You should find 2 points One is E divided by R. Here you can see it is already there. E divided by R. Can you see that? E divided by R? That is your ID. And that is VD. VD is equal to E. From where we got that? Above equation. See? VD is equal to E. E is 10. VD is equal to E. And your ID is equal to E divided by R. That is your two equation that you get 2 points. That is 20. That is 10. So if you draw a line that will cut it here, that is at the Q point. From the Q point, you draw two lines. One line here, another line here. So they will intersect the axis here and here. So this is 0.78 around, approximately 18.5. That is your ID. That is also approximately. That is your solution. Wow. Oh my God. Now you look at this. Reversing the diode. When the diode is reversed, that means it is reverse bias. That time it will work like an open circuit. Remember, when the diode is reversed, that means it is not carrying any current. So it will work like an open circuit. Open circuit. So no current will go. Now here, for the series diode configuration, VD, VR, and ID. VD, VR, and ID. Find the VD, VR, and ID. So this is a series diode configuration. Your E is 8 volt. Your resistance is 2.2 kilo ohm. And your silicon is silicon diode. You know it. Now, your silicon diode take around or roughly 0.7 volt. This diode will take around 0.7 volt, right? Around 0.7 volt. The rest of the voltage will be taken by the resistance. Understood? Your silicon diode will take 0.7 only. The rest means from 8, silicon will take 0.7. The rest of the voltage will be taken by the resistance. So your VD is 0.7 volt because the silicon is forward bias. In forward bias, it takes 0.7. So your VR should be 0.7 minus from 8. So 8 minus 0.7, 7.3 volt. So your VD is 0.7, your VR is 7.3, and your ID, that means the diode current. Diode current should be the resistance current as well, because your diode current should be equal to resistance current equal to VR divided by R. So your VR is 7.3, your R is 2.2, so your current is 3.32 milliampere. So that is a very simple math. Okay, let's do a math here. This is a very good math. They have used two diodes. One is silicon diode, another one is LED, that means light emitting diode. One is silicon diode, another one is red, that means light. Okay, wait a minute. So this math is the last math of today's class. This is a very interesting math, and this is a very simple and easy math. Here they have used two diodes. One is the silicon diode, another one is the light emitting diode. That means the LED. How do I know it is an LED? You all know LED, but you do not know LED is a diode. This is an LED. How do I know it is an LED? Because there are some arrow. Can you see some arrow? I believe you can see some arrow. Here, you can see some arrow. This is an LED. So silicon takes 0.7 because you already know it, and both of them are forward bias. How do I know it is forward bias? Because see what is before silicon diode. Say they have said it is plus 12 volt plus. So plus is connected with plus of silicon. This is the plus point. This is the minus point. So this is the plus part. That means the P type, and this is the minus part or the N type. For diode, it is also forward bias, P type and N type. So both of the P type are in the same direction, and your plus 12 volt is connected here, plus 12 volt. And what is your ground or negative? Negative is here, right? So this is a forward bias. So current will flow from this. Okay. So current will flow from this point to the ground, right? So this is forward bias. Both of them are forward bias. Now, in forward bias, silicon takes 0.7 here, and red take 1.8. How do I know from here? How do I know it? How do I know it will take 1.8? It is from table 1.8. Go and see table 1.8. We will see that in the next class when we will talk about the what is that? The LEDs. Red LED take 1.8 volt. Red LED take 1.8 volt. Remember, this is the red. It will take 1.8 volt. It is a silicon. It will take 0.7 volt. So how much they will eat? How much they will take? They will take 2.5 volt because 0.7 plus 1.8. They will take 2.5 volt. Your source was 12 volt, and your 2.5 is already gone. So how much you are remaining with? How much you are left with? You are left with 9.5 volt, because your VO will be E minus VK1 minus VK2. Your E is this one, your VK1 is this one, your VK2 is this one, and that is the VO. That is after two diodes. That is your VO. VO should be 9.5 volt because 12 volt minus 0.7 minus 1.8 is equal to 9.5 volt. So if you get 9.5 volt here, and this is your resistance, right? At one point of the resistance, you got 9.5 volt. At another point of the resistor, you got 0 volt because that is grounded. So there is a voltage drop in the diode, in the resistance, that is 9.5. So okay, share again. Now, see this one. Your here your voltage is 9.5 volt. Here your voltage is 0 volt. So there must be a current flow. So that is called IR. So IR or ID, whatever you say, because this ID will flow here, right? This ID will flow here. So that is also IR. So your IR must be VR divided by R, because the VR is this one. That means the VO and VR, they are same. That is 9.5 volt. And your R is 680 ohm. Okay, how do I know VR is equal to VO? Because you have only one resistance here. At the first point of the resistance, your voltage is VO, that is 9.5. At another point, your voltage is 0. So 9.5 minus 0 is equal to 9.5 volt. That's why they have written VR equal to VO. So your current must be voltage divided by resistance. So your voltage is 9.5 volt, your resistance is 680 ohm. So your current is 13.97 milliampere. Remember one thing, if you divide volt by ohm, your current will be ampere, but they multiplied by 1000, that's why that become milliampere. Okay, stop sharing. Now I believe all of you heard, and you read these after this class, because this is online class. So if you do not read after the class, you will forget everything. Understood?
Yes, sir.
Okay, you will forget everything if you do not read. So please, I beg of you, please read after the class. Okay, now if you have a question, ask me in the what is that, in the WhatsApp group. We have a WhatsApp group, right? Ask me in the WhatsApp group, I will give you the answer. Okay, if you have a question, or okay, or while reading it or while revising it, if you face any problem, take a screenshot and ask me here, not here, ask me there in the WhatsApp group. Okay, because that is our that is our own WhatsApp group. Nobody will watch that, so we can chat. And I want, yeah.
And we are need in Google Classroom.
Google Classroom?
Yes.